Welcome everyone to the IEA Bioenergy Webinar series hosted by the Canadian Institute of Forestry. My name is Ronnie Huang and I'll be kicking off today's session. Today is March 22nd, 2018, and we are very pleased to have Thomas Nussbaumer with us today, who will present on aerosols from biomass combustion. We're also very pleased to have the task leader of IEA Bioenergy Task 32, Jaap Kopeaan, who will be opening up the session and introducing our speaker for today. To start things off, Jaap Kopeaan is the leader of Task 32, who focuses on biomass combustion and co-firing. He is the founder and managing director of Proceed Biomass BV, a contract research and development company involved in development and market introduction of bioenergy technologies, with a clear focus on biomass combustion and gasification. Jaap is also the technical director of Bioforte BV, a renewable energy service company using advanced biomass combustion technologies to sell heat and eventually power. With that, I'd like to pass it over to Jaap.
Thank you, Ronnie, for that kind introduction, and welcome everyone to this webinar again. So my name is Jaap Kopeaan, and I hope you find this webinar enjoyable and also informative. Let's see if I can go to the next slide. So yes, my picture is on the right-hand side, but I think Thomas should be on the focus of this presentation. Thomas Nussbaumer, I would like to introduce him to you. Thomas is a professor at the Luzern University of Applied Science and Arts. He has a background in process engineering with a diploma from the Swiss Federal Institute of Technology in 1984. He's a lecturer at ETH in Zurich also, and he's the owner of Verenum Research, also a contract research company on bioenergy. Thomas is also the Swiss representative in IEA Bioenergy Task 32 already for several years, and he is also the author of the report that we are currently discussing. Just one more slide on Task 32, what it is about. So Task 32 is basically one of the tasks within the bioenergy agreement, or the bioenergy technology collaboration program, as we call it nowadays. So this is part of the International Energy Agency, and within our network we've got currently 13 countries participating. You see them on the screen here, varying from several European countries up to Canada, South Africa, and Japan. And within our task, we work together in different projects, such as this one on aerosols, but we also have other projects on, for example, district heating, how to design a district heating network that is biomass fired, or co-firing biomass, or topics such as corrosion in combustion installations. We do have project meetings, workshops, conferences, and excursions. The next one, for example, will be in Copenhagen at the European Biomass Conference, where we organize a workshop on solid recovered fuels. You can find our reports on task32.ieabioenergy.com. Thomas, I would like to hand over to you from here. And I would just like to mention also, yeah, just one more. After the presentation, there will be opportunity for Q&A. So we'll get there after the presentation. So please hold your questions until then. Thank you.
Thank you very much, Jaap, for the introduction. I would also like to welcome everybody to my presentation on aerosols from biomass combustion. You see the report I provided for the IEA Bioenergy Task 32 on the right-hand side, the same title, Aerosols from Biomass Combustion. And I will now go into the content of this report, which is also available as download on the IEA Task 32 homepage, which you see here. And the content of this report is actually, the target is to give a statement on aerosols from biomass combustion. So we call it aerosol statement, which is described as a summary in the executive summary, the first 3 or 4 pages in the report. And this summary and also the whole report consists of 2 parts. Part 1 is background information, and part 2 is giving the position of the IEA Task 32. I will also follow this content in my presentation and therefore start with part 1, background, which is or the suppositions, facts and figures, which we believe are well known or true, and which are the basis actually which we will rely on. So first of all, I would like to remind that priority number 1 for all IEA bioenergy is of course that biomass is acknowledged as a renewable fuel, and it therefore can substitute fossil fuels for heat and power production, and it can do this in a very effective way with high efficiency, and therefore contribute to sustainable energy supply. So this is actually the basic target, and I will not come back on this issue anymore because now I will focus on really the topic on aerosols. And here the fact number 2 is that we all know from many experiences around the world that good, modern, well-designed biomass boilers are able to be operated and cause low air pollution. However, low air pollution are only achieved if the boilers or the stoves are properly operated. So these two conditions need to be met. This leads me to fact number 3. This means that other applications may cause incomplete combustion. And if we have incomplete combustion, products of incomplete combustion, PIC, may be emitted to the atmosphere, and these are consisting of gaseous compounds, carbon monoxide and volatile organic compounds, and of course carbonaceous particulate matter, PM. So this is true not only for, let's say, simple devices or open fires, but it is also true for badly operated wood stoves and boilers. They also can cause incomplete combustion and products thereof. So if we consider now this particulate matter, it is well known from many epidemiological and toxicological investigations that inhalable particulate matter in general, and in particulate from combustion, is harmful to health. So this is true for particles smaller than 10 microns or smaller 2.5 microns or smaller 1 micron. And all these particles from biomass combustions are mainly in the size range not only smaller 10 microns, but mainly smaller than 1 micron. So we have to deal with these particles, and we know from many investigations that it is harmful, or it can be harmful. And here is an actually recent graph from OECD and IEA on an energy poverty report, which concludes that roughly 1.5 million persons per year die from an not natural reason due to smoke from biomass. So this is even more important than malaria and tuberculosis, and it will be more important than AIDS in the near future. These are the prognosis for 2030. Now, of course, in this report, energy poverty, biomass combustion is also considered if you look at the example here on the right-hand side in the picture, where we see that open fires used for cooking indoor leads to very high indoor air pollution, and the smoke then is certainly one important reason for this high figure given here in red. Nevertheless, this should remind us that there is a potential target conflict between actually biomass as a CO2 renewable energy with a closed carbon cycle on the one hand, but on the other hand with potential air pollution which need to be avoided, of course from this wood cooking device, but also from inappropriate operation of log wood boilers, which is shown in the example here. So due to this particulate matter we have seen here so far, I've been talking about wood smoke. We also have to consider that if we want to assess combustion aerosols and their health relevance, two types of completely different particulate matter need to be distinguished. Type number 1 are the already mentioned products from incomplete combustion, so basically carbonaceous material caused by primary particulate matter as soot, or also elemental carbon, black carbon, as rather a synonym, and primary organic aerosol, TOA, including condensable organic compounds, so tar droplets. This is type 1, let's say, number 1, and number 2 is secondary organic aerosol, which can be formed if volatile organic compounds are available in the flue gas, and they can be formed in the atmosphere. So both have to be considered. Type 2 particulate matter are products which are also formed at near complete combustion, so they're not basically carbonaceous material, but primary inorganic aerosol from ash constituents like potassium, calcium, chlorine. And these kind of inorganic aerosols can be effectively precipitated without major risks, thanks to the lack of organic carbon in these particles. So we need to consider these two types, type 1 and type 2 of aerosols. Here you see a quite complex graph which I tried to prepare to summarize the main formation passes leading to particulate matter in the ambient. And you see in blue the inorganic material, so salt finally resulting as particulate matter from potassium chloride and other components, and they are formed from the inorganic ash constituents in the fuel. On the other hand, given in red are all these carbonaceous materials which may end up in the volatile phase or in the particulate phase in the flue gas if the combustion is incomplete. And we see many different pathways. There are some information which are important. On the one hand, soot is only formed if the temperature is high, however, in absence of oxygen due to synthesis. On the other hand, at low temperatures, also organic carbonaceous material remains, which might be in the liquid phase, COC, or in the gas phase, VOC. So the whole description is given in the report. I will now proceed and actually distinguish here again blue and red, these two types. And on the other hand, in red you see we have the primary organic aerosol and we have additionally secondary organic aerosol. If we distinguish type 1 and type 2 particles, we see that type 1 as a result from incomplete combustion can be formed due to potentially two reasons. On the one hand, at low temperature in the combustion, carbonaceous material in the fuel remains in large molecules which are not completely destroyed. These large molecules at low temperature remaining may form tar droplets, shown here. And the reason for low temperature can be that, for instance, we have very high excess air, so that we have a dilution of the flue gases, which leads to a low temperature combustion. On the other hand, we can also have high temperature in the flame thanks to low oxygen content in the combustion chamber. But if we have local lack of oxygen in the flame, synthesis of such carbonaceous material can form soot particles, which are shown here. So this is typically, for instance, if we have too low excess air ratio. In between, we have a combustion regime which might achieve near complete combustion, since we have to guarantee sufficient oxygen in the flame, but not too much oxygen leading to a dilution and therefore low combustion temperature. If we guarantee such ideal conditions, we can safely meet very low concentration of carbon monoxide as an indicator of the completeness of the combustion, and also low concentrations of VOC and all these carbonaceous materials, so we end up with just basically inorganic material which forms particles in the flue gas as inorganic salts. So this is some background, and the question is, of course, which are the main sources of this type of particles. Now, if we consider a well-designed automated biomass boiler, like you see a moving grate boiler here, we apply primary air for gasification of the biomass on a grate. We then inject secondary air with high velocity, so we can achieve near complete mixing with the combustible gases. And we then have a consecutive post-combustion chamber at high temperature, which achieves near complete oxidation of all gases. So only after the combustion has been completed, then we see the consecutive heat extraction in the heat exchanger. So we avoid any kind of quenching and low temperature before all the combustion has been completed, which will finally end up in the situation that we have very low concentration of all carbonaceous material, and in the end, in the particulate matter in the flue gas, we expect actually more than 95%, maybe even 98% and more inorganic material with just very low concentrations of soot. So this is true for near complete combustion in well-designed and well-operated biomass boilers like shown in this example. On the other hand, if we do not fulfill all the requirements, if we have low temperature since we apply wet wood in a small stove, or if we have air throttling in a stove, or if we have any other situation which is non-ideal, we find this high concentration of carbonaceous material forming soot, black carbon, forming this COC, tar, and also volatile. Now, if we look at actually the importance of these different type of particles, we again need to distinguish between organic material and inorganic material. For all this kind of organic substances, it is well known that these are potentially harmful. This is also known from smoking. And it has been shown with many investigations. Here is one example of an investigation from 2008 on toxicology by Kochbach et al. And you see two indicators for toxicological effects. And we clearly can see that with increasing organic carbon in combustion particles, we see an increasing health effect. So this is one example of health investigation on combustion particles. Another example from an investigation in my group in Switzerland some years ago is an investigation where we made a comparison between particles from a badly operated wood stove, which forms soot and also tars. And we see that here the cell survival rate decreases to 50% already at very low concentration if we have these particles in the cell medium. If we then apply particles which consist mainly of soot without major concentrations of these organic material, we see that we still found a significant influence on the cell survival. However, it is obviously less toxic than these compounds which also have high concentration of organics. The third example shown here are particles which are found in an automated wood boiler, so they mainly consist of salt. And we see that again, the toxicity effect is far smaller than with all these type of organic material. We also need to say that in this investigation there was even an effect just from the fibers from the filter, so this might be due to sampling. We just can say we have a far lower effect than for all these kind of particles which result from incomplete combustion. Now these information were true for this primary organic aerosol, and there is also indication that secondary organic aerosol can be harmful. This is known from various investigations, but here is a recent investigation just reported in 2017, which is true for aged organic aerosols from different wood combustion devices. And it clearly shows that also here the reactive oxygen species as an indicator again for toxicity effects. is increasing with increasing aged organic aerosol emissions. So this also indicates the secondary organic aerosol, which is aged due to ultraviolet radiation, actually is also very important for health effects. I would like to comment that you need to note that this is the only information, this graph and this literature given here, which is not available in the IEA report, because this investigation was published just after our IEA report came out. So this is the only graph which is new here. Everything is in the report. With this, I would like to summarize which are the measures to reduce particulate matter or avoid increased PM. It seems clear that priority number one is primary measures to avoid type 1 particles from incomplete combustion. And for this, we need to achieve near complete combustion by actually adjusting an appropriate air-to-fuel ratio, and additionally fulfill the 3T rule, which means sufficient turbulence for well mixing the gases and the air, sufficiently high temperature above 800 degrees for sufficient high reaction rates, and sufficient residence time, more than 0.3 to 0.5 seconds, to have a near complete burnout. Now this is quite easy to say, and it is also possible to fulfill these requirements. On the other hand, requirement 2 is that we just need to make sure that we avoid any non-ideal conditions. Now this is also easy to say, but hard to fulfill, because during each startup we cannot fulfill the temperature rule here, so the startup is always related to increased emissions. In addition, the batch size should be appropriate for the wood stove or wood boiler. When we look at startups, we see here an example in a wood stove. We see that for bad startup we can have very high emissions, while if we make a reasonable startup, shown here, with just small logs on top and ignition from the top, we can reduce the particulate emissions significantly compared to bad startup. Nevertheless, we will always have increased emissions during startup compared to stationary conditions. So this is startup. Next point is fuel conditions, fuel moisture. It has to be dry for small scale residential appliances, because else the temperature is not sufficient. This is well known. And another issue is the fuel size, the log size, if you apply wood stoves. Here is an investigation from Germany which shows that we have reasonably low emissions if we have appropriate log size. However, if we have too small logs, we have increased emissions given here. And in addition, the burn rate also needs to be adjusted. There is always, let's say, an ideal burn rate. In some cases it might be in a certain range, but typically if you go to very low burn rate, we have an increase of emissions, and we also find increased emissions if you go to far too high burn rates. So the burn rate also needs to be adjusted. Finally, air throttling needs to be strictly avoided to avoid smoldering conditions. And for this reason, we, for instance, highly recommend the application of heat storage tank for logwood boilers. So these are the main primary measures. There are also secondary measures which are available: catalytic converters in wood stoves, precipitation, for instance, by electrostatic precipitators in boilers, or also small wood stoves. This can be applied. However, we need to also consider that catalytic oxidation and also ESP usually need a certain temperature to work properly. So we have a limited availability during startup very often. And in addition, there might be other drawbacks, like, for instance, if you have soot particles in the flue gas and we have a precipitation in the ESP, there is a potential fire risk in the ESP. So for this reason, primary measures are of high priority, and secondary measure basically as an add-on or as an option. Now if we look at the type 2 particles, we also have primary measures and secondary measures, but I here start with the secondary measures because if we are able to achieve near complete combustion in automatic boilers, we can easily apply precipitation by ESP or also fabric filters for dry biomass. And this can be effectively applied if we have low concentration of particles from incomplete combustion. So this is well possible for automatic boilers. It is also available for small-scale residential wood combustion. However, it might be critical if we have high concentration of products from incomplete combustion. So for small-scale, primary measures are also crucial. We should avoid critical biomass fuels, so we should apply low ash fuels and low moisture content fuels for small-scale boilers and stoves. So the ash content means that we should have good conditions in harvesting, avoiding high concentrations of bark, for instance. And for small-scale wood chip boilers, also sieving can be applied for the wood chips. These are the measures to reduce PM. With this, I would like to conclude part 1 and come to part 2. The position of the IEA Task 32, summarized in 7 statements which were agreed by all 13 member countries. Statement 1, global mortality due to cooking on open fires and simple devices shall be reduced. This can be done either by replacing open fires with wood gasifier stoves, or else other alternatives for cooking need to be applied, like gas, solar, and electricity. Statement 2, for manually operated devices, an appropriate operation is crucial. The fuel needs to be adopted with respect to moisture, size, and ash content. The startup should be ideally done, so for instance for stoves and fireplaces, very often from the top ignition is favorable. Then the amount of wood needs to be adapted to the size of the combustion chamber, so the amount of wood for one batch in a stove or in a boiler. The air should be supplied in a reasonable amount, so not too much air and not lack of oxygen. So finally, of course, no air throttling should be applied. These are the primary measures for an appropriate design, appropriate operation, And in addition, secondary measures can be applied, catalytic converters and ESP. They are also applicable, but we consider them as an add-on to near complete combustion. Near complete combustion is priority target. Statement number 3, if we have high requirements for fuel, standardization of fuels is favorable. The same is true for devices and for test methods. All these can assist target-oriented development. If we look at the test methods, they should not only consider very ideal operation conditions, but they should also consider something like real-life operations. Statement 4 is that it is clearly shown that automated biomass combustion plants for heat or power can achieve very low organic pollutants if they have advanced combustion design and control technology. And in addition, automatic combustion enables efficient precipitation of all remaining inorganic particles. So this can be guaranteed. Nevertheless, also during plant planning and later during operation, quality management and plant monitoring can further assist ideal operation and low pollutant emissions during real-life application. So statement number 5 is a logical consequence that Bioenergy Task 32 supports automatic boilers if they are equipped with control technology and precipitation. Residential applications, however, are also supported, but only if strong quality criteria are met. So this is certainly guaranteed if we apply wood pellets in modern pellet boilers, for instance. On the other hand, very simple and old-fashioned appliances like open fireplaces or old logwood boilers without heat storage tank, etc., are discouraged, especially in urban areas, because they can cause local air pollution. To consider biomass aerosols, we have seen that two different sources of PM need to be distinguished. Type 1, primary and secondary organic pollutants, including soot, which result from incomplete combustion and which exhibit adverse health effects. Type 2 are inorganic particles, which reveal lower health effects. So for future regulations, it should be considered that the health effect, the health relevance of these two types of particles are different. And in addition, the regulation should also take into account potential secondary aerosols, which can be done, for instance, by emission limit values, also for precursors like volatile organic compounds. So the final statement number 7 is that the IEA concludes that an exchange between the stakeholders from research, industry, and authorities can certainly also assist the advancements for an increased use of biomass as energy carrier and a certain high air quality standard. So with this, I would like to thank all you for your interest, and I would like to acknowledge the IEA Bioenergy Task 32 and also the Swiss institutions which were funding our investigation. Thank you very much for your attention. And with this, I would like to give back the phone to Jakob Pean to moderate the question and answers. Thank you very much.
Thank you, Thomas, for this nice presentation. And I was just wondering if there are any questions. I think there's an option to identify yourself and raise your question. There's an option to type this in the chat box that's now appearing on the screen. So please go ahead. If you have a question, you can type it there, and we will try to answer it. Also, there's an option. We're quite interested to see who is actually participating in our webinar. So please, if you have the opportunity, just click the right box here on the screen, so that we know the type of audience that we're getting. I see several people are typing questions, so that's good. Let's see what comes up first. Shahab, I think you're typing if there are any specific recommendations for wood pellets. Thomas, yeah. Can you answer this question?
Thank you for the question. If you start with wood pellets, I mean, usually it's the other way around. One of the most important recommendations is that as soon as you switch from manual operated boilers and stoves to wood pellets, you have a big advantage that the process is then automated. So if you have a well-designed wood pellet boiler, we usually can guarantee that even in practical operation, they should be well operated at near complete combustion with low pollution. So usually it is clearly seen as an, let's say, an advantage. Maybe just one side remark. When we are talking about wood pellets, we usually assume that it is really just the natural wood, not any demolition wood or so, which should be used for wood pellets in small-scale boilers. And it should also be, well, an advantage would be to use bark-free sawdust, or if you use wood, not just very high concentration of bark, etc. But usually wood pellets is a favorable fuel for also small-scale application. In large-scale application, of course, wood pellets are also the most favorable biomass fuel, but in large scale also other biomasses can be used. So this is my answer to question number 1 on wood pellets.
Okay, I hope this was clear. There's one more question. I just pick one of them here from Gabriel, which is on commercial application of small-scale biomass combustion. So commercial wood stoves like bread baking, pizza baking, etc. The traditional commercial wood burning applications. We didn't do any research on this, I think, Thomas, did we?
Well, I see the next question. Can we figure out why most stove manufacturers are not implementing lambda sensors? To remove
we can also do that one.
and different fuel specifications. Yeah, okay. I think I'll try to give an answer on that question.
Okay.
If we are talking about wood stoves, the question is clearly about wood stoves. I think it is not impossible to apply lambda sensors and control technologies, but still it is rather limited compared to a boiler. And one limitation is that usually wood stoves should be operated without ventilators, so just natural draft. So with natural draft, of course, also the control opportunities, even if we apply lambda sensors, are rather limited compared to the situation that we also apply ventilators, where we can control the speed of the ventilator, or where we can control the draft and valves, etc. So we also think that even for stoves, although sensors might be helpful, primary measure like ideal design of the combustion chamber is the first step which we should take. Then, yeah, well, can anyone help? I think this is a question to the audience. If there can be more pressure. So I try to answer this and maybe can go to the next question, or Job, what is your recommendation?
Yeah, I was wondering on the question by Gabriel Chevreville, if you have any recommendation on commercial wood stoves. So we didn't cover that, I think. On the pizza ovens and bread baking and so.
This question here, go to the next one. Wood stoves, commercial wood stoves for like pizza baking. Yeah. Well, this is a difficult one.
I would say basically the same principles apply as with the normal wood stoves, that we need to look at particle emissions and so. But are you aware of any studies on this?
Maybe two comments. For bread baking, there are, of course, opportunities to use actually automated pellet, how do you call this, furnaces, which actually supply the hot flue gases after combustion to the room where you have the baking process. This exists commercially, so I'm aware of several such applications. For instance, here in Zurich downtown, where there is a bakery which has really baking, which is preparing the bread by wood combustion, and they had to switch to some solutions which are less pollutant because they're downtown Zurich. And they initially wanted to go for an ESP with the existing wood combustion device, but they finally decided to replace the old stove by a new one, and the new one is fired with pellets, automatically fired. So this exists for bread baking. For pizza stoves, I believe that certain kind of secondary measures might be more reasonable. The drawbacks I mentioned for ESP and others, if you have particles which are combustible, these drawbacks have to be considered. So there are certain fire risks which need to be considered, but still it is possible to apply these also for pizza stoves. And there are certain applications like this.
Okay. Then the next question is about woodlock stoves, which I think you mentioned the fact that old woodlock stoves can be particularly polluting, and but we also know that there has been significant progress in the design of woodlock stoves that have to meet more and more strict emission limits. Can you say something about this, about modern woodlock stoves?
If we see the modern small-scale logwood stoves, we can clearly see that if you have an ideal operation, the emissions are low. It is really the type of operation which is crucial. So the point is that here we have a problem that many persons who apply such stoves are not doing this correctly. They start up and they have often too large batches of wood in the stove, or they apply anything else except just ideal size and moisture of logs. So if you go to the test results from test bench, you see that if you do it properly, also small log stoves can have low emissions. So it is really, I would say, the main problem of how to guarantee that people do a correct operation. This is my answer on the manual new log stoves.
Okay, thank you. Then the next point was from Terence Sauvé. I think that refers to his previous question, so we can skip that one, I think. The next one was from David Kempsey on automatic boilers. If we know something about pellet size, if you make pellets from a particular type of biomass, like palm waste biomass. This is a rather specific question. I don't know if you would like to answer it.
This in detail, certainly not. I would just like to maybe give one other information here. It's my personal opinion, but if you say, if you are asking about the pellet size, I would rather say the boiler size is important. So let's say the pellet size needs to be in a certain relation compared to the boiler size on the one hand. And on the other hand, if you go to any biomass fuels which are more challenging than just native wood, which is the case for any waste from production of fruit or palm kernel, etc. My personal recommendation is that such type of fuels can certainly be handled and burnt efficiently and with low emissions in any type of automatic boiler from a certain size. Now, if I say certain size, I mean it should not be a residential application. It should rather be 1 megawatt or larger whatsoever, where you can apply control technology and electrostatic precipitators, etc. And if you do so, I think the pellet size can then be, of course, normal pellet size like we apply for wood pellets, where you have maybe 10 millimeters in diameter and 30 millimeters in length. But for larger boilers, the pellet size can, of course, also be far bigger. This is not a crucial issue if you have a reasonable boiler size for this type of fuel. This would be my answer here.
Okay, thank you. The next question was about the current eco-design limit of 5 grams per kilogram for logwood stoves, if that should be lower. So this is regarding the emission limits in eco-design for wood log stoves, which is applicable after 2022, I presume.
Mm. Well, this is again very detailed, specific question, and I do not have the figure exactly now here. If I calculate this to the concentration which I usually deal with, but I have a certain idea. I usually consider milligram per cubic meter or milligram per megajoule. But anyway, if I remember correctly the calculation, I'm convinced that this emission limit value is quite low. So I do not think that the point is to have lower emission limit values which need to be achieved on the type test bench. The main issue is always that you have to make sure that the standardization test here should resemble real-life application to avoid the performance gap between type test and practical application. This is the issue. So rather have 5 grams per kilogram, but achieve this also in practical operation than, let's say, half the emission limit value on the test bench, but you have something completely different in real life. This is, for me, more important than having a very, very low figure as emission limit value on the type test.
Okay. I hope that point was clear. Then the next one is by Michael Wild from Austria on user awareness. And I think you already mentioned, Thomas, that the influence of the user is critical, particularly with small-scale applications. So what's your opinion on this? Should we raise awareness, or what measures could be effective in this?
Yes, I fully agree. I tried to point out that the operation type is actually for manually operated wood stoves and boilers really the major issue. I did not go into detail on the influence of the operator of automated plants, because also there we have a very strong influence, particularly by which fuel type is used, but also whether there is a reasonable maintenance which actually guarantees that also automated boilers are well operated. This is also true. How else? Usually we have far stronger control by authorities with the large-scale automated plants.
Okay. Then the last question that's here in the chat box is about primary mitigation measures. I think you talked a lot about organic PM, but this is about inorganic PM. Do you think that additives could help there? That's the question.
My personal opinion, about which is based on experiences in my research group a little bit, but there are more extensive investigations, for instance, in Sweden and in many other countries. I remember we have discussed this in many seminars. So the conclusion there was that, yes, you can achieve a positive effect by certain additives. However, the effect is rather low, although you have a rather high cost if you look at the additive you need to add and if you look at the handling. So it is not very cost-effective measure, because the effect is not like reducing the emissions by 95% or so, but you usually have quite low effect. So it's already a significant effect if you reduce the emissions by 50%, but if you have a very high cost for the operator, but you end up with very low reduction, I think it is not a very promising way to go.
Mm-hmm. Okay. Then one final additional question popped up by your Calvin, and I think he agrees upon what you said about real-life testing, that this is important. His question is what this could look like, and I think we can refer also to the two research projects that have been finalized over the past couple of years, like the Be Real project, and there's also a project in Austria, I think that covered this area on stoves. So I think there are new test methods being developed that could tackle this. You would like to say anything more about this, Thomas?
Let's say I would agree that we just can try to improve the test, and we will never be capable to actually consider all possibilities of real life. This will never be possible.
No.
Of course, we, for instance, have to make sure that people need to use dry wood in small wood stoves. So this cannot be just adjusted in the case that we say, okay, also in the test bench we need to operate the stove and the boiler with wet wood. It should be capable to do this. We know it is not possible. So here we rather should go for really not only education of the operators, but in case that there are really severe single sources of high pollution, of course there also need to be some restrictions by the authorities which are implemented. So this is the answer here. And there was now a last question coming on a slide which I showed from Hans
Hartmann, I think.
And this team, did they measure the excess air ratio? Yes, they certainly did, but I have to acknowledge that I don't know the figures by heart. So I just can say they were investigating the size of the logs put into a normal stove, and if I remember correctly, they tried to operate the stove in an ideal way, except they changed the log size. So I don't know if this answers the question, but the number or the figure of the excess air ratio is certainly reported in the report from Hans Hartmann and co-authors, or it is even available in the conference slides, which are available as download from ETH conference on combustion-generated nanoparticles. We had also a session there, which I was organizing for IEA Bioenergy Task 32, together with Jaap Koppeaan. So we had a session there, and there were several presentations. They are available on the ETH homepage, the conference on combustion-generated nanoparticles.
And also on the Task 32 website.
Okay, cribwood.
So
okay, interesting.
The cribwood debate.
Yeah, I'm not aware about this.
Yeah, I think this has to do with how to light the stove, I would guess, but
scrap wood, so this would be actually like certain kind of demolition wood, or I don't know exactly what is meant with scrap wood.
I would say this is the, okay.
The standard tested fuel. Ah, okay. Okay, yeah. I see. Yes. I think I tried to answer these questions.
Yeah, please go ahead, Thomas.
Mafra is typing.
Yes, maybe we get some more background on the question, because
okay. Last question, Earl Plain. Will your presentation be available for download? The answer is yes. Thank you for your interest. We will make a PDF with all slides available. And again, I would like to remind, the content is more precisely given and described in the IEA report, except one slide on secondary organic aerosol, which was not yet available when we published the report. But nevertheless, the whole presentation will be made available as PDF on the IEA homepage. So I would like to thank very much for the interest and the audience, and say goodbye in case that we are now done. Or Job, what is the idea?
Yes, I will close it. I think. Thank you, everyone, for listening to this this webinar, for attending, also for the questions that we got. I would like to just remind you also that the Task 32 will keep on working on this topic of aerosols from biomass combustion. It's identified even as a more important topic in the next work plan that will start in 2019. So we will continue to work on this. Please follow the work that we are doing, and I hope you find it useful. With this, I would like to close this session. Thank you again, and goodbye.